Hello. This will be a demonstration of Proposition 23 from Book 8 of Euclid's Elements, which says that if four numbers be in a continued proportion, and the first is a cube, the fourth also will be a cube. This is much like the previous proposition, 8.22, but instead of square numbers then, there are cube numbers now, and instead of a 3-term continued proportion, there's a 4-term continued proportion. With that said, we are given four numbers A, B, C, and D that form a continued proportion, that A is to B, just as B is to C, just as C is to D. We're also given that the first number A is a cube number, and what we want to prove is that the fourth number D is also a cube number. Now, between A and D, there are two mean proportionals, namely B and C. We were given that information, that A is to B, as B is to C, as C is to D. So that B and C are two mean proportionals that lie between A and D. We also know from Proposition 8.21 that if two mean proportionals fall between two numbers, those two numbers are similar solid numbers. So that because there are two mean proportionals between A and D, the two numbers A and D are similar solid numbers. But we were given that the number A is a cube number, and being similar to D, D therefore also has to be a cube number, which is what we set out to prove, which means we're done with the proposition, therefore, etc. Q, E, D. Very straightforward, very short, like the previous proposition again, 8.22, but instead of square numbers, there are cube numbers. This last step here can be explained in a similar way, both by a geometric intuition, but also a statement about proportions drawing from the definition of similar solid numbers, definition 7.21. You can understand this as, because A is a cube number, we can represent it as a cube, like this, like that. That will be it. The number A is a cube number, so we can represent it as a solid that is a cube. But any other solid, which we know D is, any solid that is similar to a cube also has to be a cube. So because D is a solid that is similar to A, and A is a cube, D also has to be a cube. It will look something like this, right? Like that. So you see that both A and D, in order to be similar, and for A to still be a cube, D also has to be a cube. There's also, again, a statement about proportions that supports this. So we know with cube numbers, their sides are all the same number. So we can represent the sides as A, and A, like that. And we know that these three sides are going to be proportional to the sides of D. That A is to the side of D, just as A is to the other side of D, just as A is to the third side of D. But for this to be true, the three sides of D all have to be the same number. So that A can be to D, we'll call that the side of D, that A is also to D, just as A is also to D. In order for A to be a cube, all of its sides have to be equal. In order to be similar solid numbers, this proportion has to be true. So D, those three D's there, the three sides of the cube D all have to be equal to each other as well. And we know that a number whose three sides are equal to each other is a cube number. That's the definition of a cube number. So because the three sides of D are equal to each other, they have to be. D is therefore a cube number. That's all I've got to say about this proposition, so I'll end the video here and move on to Proposition 8.24.